I feel incredibly privileged as an RF engineer to give a talk somewhere like this. I've given lots of talks in lots of places, and it's always really nice to stand somewhere that's very inspiring as an engineer. We had some school children in earlier, and I gave a talk to them, and this is the type of place, to me, that inspires the next generation. So if we want to inspire the next generation of engineers and scientists, you need to keep somewhere like this and make sure that people do actually have the opportunity to come and see the wonderful work of Marconi and the company and the people that he was privileged to work with as well.
Hear, hear.
I digress, I'm sorry. I'd like to start with the motivation behind a lot of my talks. I have a baby. She's 16 months old, and like any 16-month-old baby, she forget the plastic toys, anything brightly coloured. What she wants to play with is the remote control for the TV and my mobile phone. And so she was playing with it a few months ago and dropped my mobile phone. And I was like, oh man, I hope she hasn't damaged it or hasn't broken it. And my friend who I was with said, well, it's okay, isn't it? Because you can just get a new one. Just throw it away and get a new one. I was like, wow, have we become such a disposable society that a mobile phone that might be damaged a little bit, but actually works perfectly well, I'm just going to throw away because it's so easy to get another one. This thing that I have in my pocket has more computing power than the computer that landed man on the moon in the Apollo mission, and I'm just going to throw it away because it might be a bit damaged. And so it made me think, wow, are we such a disposable society? And do we take this wireless communication for granted so much because it's so embedded in our everyday life? And so I'd like to take you on a journey of what I think we do take for granted in wireless communication, and how we're using wireless communication and the work that largely was started by Marconi to solve some of the engineering world grand challenges of today. And I know I always asked why a lot when I was a child, a really young child, and maybe that's what it was. But then I sort of thought, well, actually, that's no different to any other child that I know now. My 16-month-old can't talk yet, but I'm sure probably after the word no, the second word she'll use is why. And it's a word that I think every child uses, that curiosity that children have. Why this, why that, why is the sky blue, why is the grass green? And I used to drive my parents mad with it, and I'm sure everyone in this room has probably driven their parents mad at some point, asking all those questions. That's why I'm a firm believer we are all born scientists. Whether or not we choose to take and develop our scientific knowledge is up to us. But we are all born scientists because we all ask that fundamental question, why, which is the fundamental question to a scientist. Now, luckily for me, I did listen to my teachers at school, and I studied astrophysics at university. And throughout my studies and early career, I continued to ask why a lot, but then I realised I was always following that up with how. How do things work all of the time? And I realised after a while that this was actually engineering to me. So the why is the scientist in me and the how is the engineer. And to me, of course I'm biased, but we're all born scientists, we can all become scientists. It takes that next level to become the engineer, because you have to ask how things work as well. And I think it's a really appropriate place to do a talk like this, because that's what Marconi must have been doing. Lots of people told him that transatlantic wireless communication was impossible. Science made it impossible. That whole why he had, why can I do this? But he also had the how. How can I do this? And unless he had that in him, he probably wouldn't have done it, because he would have listened to all the scientists who said, scientifically, you can't do this, it's impossible. So for me, the why is the scientist, the how is the engineer. So I continue to use my science and my engineering in my job now to help solve one of the 14 engineering grand challenges. I engineer the tools for scientific discovery, and I use radio waves to do this. And I'm sure many people in this room, the collective intelligence of this room must be astounding. So I'm sure lots of people know the electromagnetic spectrum. So I'm using around the radio waves up to the microwave region here. And we are bathing, no matter where we are bathing in this sea of electromagnetic waves. And of course the energy will change in the photons, depending on if we're at radios, which have lesser energy, all the way up to cosmic rays. And because we've known about the electromagnetic spectrum and EM induction for quite a long time, since Faraday. So Michael Faraday first demonstrated electromagnetic induction in the 1930s. And then, sorry, 1830s. Thank you, I was checking your away. Yeah. Yes, 1831 it was. Yeah. And then James Clerk Maxwell came along and then really laid the theoretical foundation for electromagnetics. And I was saying to some of the students earlier, if you study physics or engineering, this man becomes your best friend when you're at university, because the four Maxwell's equations are absolutely fundamental to any person studying physics or engineering. But it was all very heavily theoretical. So then Heinrich Hertz came along and demonstrated just over a very, very short range that wireless communication was possible. But of course we all know Marconi is very much the father of wireless communication, demonstrating over a few kilometres and then transatlantic in 1901. He then continued to increase this distance from transatlantic to the Bay of Sydney, some 4,000 kilometres away. Now this represents a 2,500-fold increase in the distance covered by wireless communication in just 6 years. It's absolutely astounding what that man and his team were able to do. And this gives the idea of the rapidity in which Marconi was able to generate and to improve this world communication system using wireless technology. And the discovery of wireless technology and using data to transmit, or air to transmit data, represents a widespread feeling of a link between wireless communication and radio astronomy, which is where I do some of my work as well. And obviously it's not a direct link. The birth of radio astronomy has to be linked to Carl Jansky in 1932. Carl Jansky was actually working for Bell's laboratories, and Bell's telephone laboratories. And it's one of those serendipitous sort of moments where he discovered that this radio interference was actually probably coming from a celestial source. He was doing some measurements with a 40-meter wavelength antenna at the time. But this study of local disturbances, these local interference, was important in this rapid development of radio communication, which has been geared by Marconi's discovery. And I'd like to thank Chris Neal for sending me this newspaper clipping. It's an absolutely amazing article that Marconi talks about wireless communication reaching to all in the universe, all with a capital A in the universe. So it discusses Marconi's views of communicating with the stars. Now Harold Begbie, the guy who's interviewing here, asked Marconi what he thought, if he thought radio waves were eternal. And Marconi, I'll just read you what Marconi said. Marconi replied, "Yes, I do think they're eternal. Messages I sent off 10 years ago have not yet reached the nearest stars. And when they arrive, why should they stop? That's what makes me hope for a very big thing in the future." What is this? asked Begbie. Communication with intelligence on other stars. So Marconi is already thinking about what this could be in the future. So perhaps it's not that surprising that Marconi became the president of the CNR, the Italian National Research Council, which established the Institute for Radio Astronomy and took over the running of the Northern Cross, which is the radio astronomy facility near Bologna. and I've been very privileged to work with some of the guys who work at the Northern Cross in Bologna. So he became the president of this CNR, and when he did, it became the leading Italian institution in the field of radio astronomy research, and still is that today. So many of the things that Marconi has done with wireless communication, many of us will share a passion for in our own different ways. I share the passion of that newspaper clipping of trying to use radio communication to understand our universe, including how it all began in the universe with the Big Bang, not the TV show. The Big Bang was when the universe exploded. There was a Big Bang, and there was a very specific temperature. So around 13.8 billion years ago, the universe began, and there were tiny fluctuations in this radiation, in this temperature. And what we want to do to understand not only where we've come from a universe, but where we're going, and a lot of the fundamental cosmological and physical parameters of the universe, we need to understand this radiation. Now, this radiation, since 13.8 billion years ago, has stretched in time. And so, over time, it's stretched into the microwave frequencies. And so now it's called the cosmic microwave background, the CMB. And this CMB is something that you can see here. And it's something that we really want to know in a lot of detail how this looks. So what you're seeing here, and it's a really strange thing to get your head around, but it's a map of the oldest light in the universe. So this is the universe, oldest light. So the light from 13.8 billion years ago. And the differences in this colour map represent tiny fluctuations, tiny fractions of a Kelvin fluctuations in temperature. And they're very important because those tiny fluctuations represent the seeds of everything that's created in the universe. So whether that part becomes a galaxy or a star or dark matter will depend on the tiny temperature fluctuations there are. So we want to be able to map the CMB, this cosmic microwave background, to a very high degree of accuracy. Now, as Ross said earlier, I worked at Jodrell Bank Observatory, which, if you don't know what it is a 76-metre radio dish, 76-metre diameter radio dish in the Cheshire Plains. And I felt very privileged to work there as a junior engineer. So I finished my astrophysics, realised that I didn't just want to do theoretical work, I want to do a lot of practical work. And sort of realised, not quite too late, I mean, I definitely should have done engineering at university, but at the time, the careers advice wasn't the same as hopefully it is now. So I started as a junior engineer because I was much more interested in the practical, the how, not just the why. And one of the projects, the very first project I worked on was to map this cosmic microwave background, the CMB. And I worked on a project called Planck. Now, Planck is, or was a spacecraft, and it was to map very accurately the CMB. It was a project between NASA, North American Space Agency, ESA, European Space Agency, and it was a very big team, so a lot of us worked together on it. So what we see here is the actual instrument. So that the gold part there, the yellow part there, is the actual instrument itself. Now, I worked on what was called the low frequency instrument. So anyone who's worked in the radio domain, the low frequency instrument on here was 33 gigahertz, which doesn't feel particularly low. But that was the low frequency. The high frequency instrument was fractions of terahertz. So there was a range of receivers on there. I worked on the LFI, the low frequency instrument, at 33 gigahertz, 27 to 33 gigahertz. And so a lot of us worked on this together. Obviously, the rest of what you see here is just the spacecraft to actually get the instrument to where we wanted it to be. The place we wanted it to be was a place called L2, Lagrange point 2, which is 1.5 million kilometres further away from the sun than we are here on Earth. And it's a very specific point in our system, in that the RFI, the radio frequency interference, is actually very low there. So if you imagine the signal you're trying to retrieve, effectively from 13.8 billion years ago, is very, very weak. You only want to amplify that signal, you don't want to amplify any noise or any interference as well. So getting it out to L2, where the RFI, the interference is very low, was what we needed to do. So it went out there. It actually took a lot more data than we thought it was going to take, so it was a lot more successful than we originally thought it would be. So it stayed there a lot longer than we thought. But all the time, what it was trying to do was map this cosmic microwave background. So this is what the best map looked like before we embarked on Planck. And this is what it looked like afterwards. So you can see the amount of detail is much, much more. And like I say, that's really important, because not only for the sort of cosmological parameters, the sort of fundamental physics that this draws on, we're able to now map the universe to sort of say, well, we can see so much more detail here, therefore where we only thought there might be just galaxies or just stars, there is a lot more structure than we actually thought there was. So it's really important from a science point of view. And of course, this is all wirelessly communicated. You can't wire up to Lagrange point 2, 1.5 million kilometers away. But it's not just science that Marconi's work has been crucial for. I do work on big data. So if you think about the big ideas in technology these days, so the idea of big data, smart data, and the Internet of Things, they are very, very big, not only in the world of research, but in the world of commerce and industry as well. So the Internet of Things is sort of the latest big craze, the IoT, you hear it a lot. Every 2 days, we create as much information as we did from the dawn of civilization up till 2003. That's according to Eric Schmidt of Google fame. So he thinks that's something like 5 exabytes of data. So let me repeat that. We create as much information in the last 2 days as we did from the dawn of civilization up until 2003. This is why they're calling it big data. There's a lot of data, and it wouldn't be possible without radio waves and wireless communication. So the whole of this industry relies on this work. Now, one question I hear a lot from some skeptical engineers that I work with is, isn't the Internet of Things just a big hype? I mean, is it really there? Does it? And to me, I always say to them, well, is it a hype? Well, actually, it doesn't really matter if it is. That's because, to a large extent, it's a self-fulfilling prophecy. And in this way, it's sort of similar to Moore's law. Now, many of us might know that Gordon Moore's prediction of doubling of transistor technology every 2 years wasn't a law per se, it was more of a goal that became the organizing principle behind the entire semiconductor industry. So the Internet of Things, to me, is a bit like this. It's a collective goal of every industry to add intelligence, to add data and connectivity into everything that we do in a wireless sense. And billions of pounds are being invested in this every single year to make this happen. So it's almost inevitable that it will happen. And now we're connecting all of these things on the internet, this Internet of Things, and we're wirelessly connecting them all in a way that will have a significant impact on the way we farm, the way we fly, the way we design cities, and so much more. So I'd like to share with you some of the projects that I'm working on, and how Marconi's wireless work is helping to solve one of the 14 World Engineering Grand Challenges that I work on, engineering the tools for scientific discovery. For instance, more than 2.8 billion people are still affected by water scarcity. And that number will only increase as the need to feed a growing population also increases. Now, there are a number of projects that are trying to implement subsoil sensing technology. So this is to bury things in the soil that measure soil parameters such as the moisture, the temperature, and nutritional ingredients needed for crop growth. So what this project is trying to do is integrate RFID technology, radio frequency identification technology, and subsoil sensing technology. So what we have are wireless nodes buried in the soil, and they are taking all of this data. The added complication about this is that because they're buried in the soil where crops are growing, you don't want the nodes to have a battery, because if the battery leaks, that's very bad for the soil and the crops. So these nodes have to be capable of harvesting the energy from the electromagnetic spectrum, which is generated from the RFID reader sitting on the tractor. So what happens is these nodes then take the measurements, send that information wirelessly to the tractor, and then that information, along with some positioning information, GPS information, allows the farmer to determine what action to take based on the results that they've got. So the idea is to help tackle the challenge of world food and water shortages by shifting towards this model of precision agriculture and just, for example, spraying water where we actually need it rather than spraying a whole field because we think the whole thing needs irrigating. Or consider jet engines. Aeroplanes are mission-critical vehicles, and as such we want them to be safe, reliable and efficient. So during development, engines such as this are instrumented with hundreds, sometimes even thousands of sensors, and they are monitoring things in the engine such as the temperature, the vibration of the actual engine. And currently these are all hardwired to a data acquisition unit. But because they're hardwired, they're inflexible, they can be expensive to set up, and they're also susceptible to cable and connector faults. So what many companies want to try and do is shift towards a wireless solution for this, or a wireless sensor network solution. So consider a jet engine, and consider putting a wireless sensor network in that engine to monitor and measure data in the engine. And consider adding a node to that engine was cheap, quick, and reliable. Very simple to do, so you didn't have to have very experienced engineers to do it. Now the amount of data that we can get from this engine can be increased because we have more nodes taking more data. The more information that we can get from that engine, the more likely we are to be able to develop the next generation of much more efficient engines. So we're trying to use wireless sensor networks to improve engine efficiency, so we're reducing the carbon emissions around the world. A third example is that of the built environment, using wireless technology to help the visually impaired navigate safely through buildings. Now, in the response for the need to give the visually impaired equal access to public buildings, the use of Braille became a legal requirement in many countries, including the UK. And so what we all see are Braille signs affixed to many things in public buildings, lift panels, top and bottom of flights of stairs, etc. But if you think about it, for a visually impaired person, there is an inherent challenge here, and that is to actually physically locate the Braille sign in the first place in order to read the information by touch. And so it's one that leaves a visually impaired person naturally very frustrated. So we're trying to use wireless technology, and actually RFID technology, to help with this. So what we've done is take the Braille signs around the building and then embed an RFID chip in each of these Braille signs. Now these are RFID tags, or chips, have a unique identifier number, so that when the visually impaired person enters the building, all of the information can then, from all of these Braille signs with the embedded tags, can now be downloaded onto an app on their smartphone. So now the app on their smartphone talks to them as they enter this building and is able to tell them exactly what they need to see or touch around this building in order to navigate safely through it. So for example, you will take 1.5 steps and there will be a step down. The toilets are 3 meters straight ahead of you, etc. Now we pilot this in my building. It's not my building, I'm sure it was. Building that I work in at Manchester, and it's a very old building, Victorian building. And if you can navigate around this, you can definitely navigate around anything. So it was a very good building to pilot this in. And it, again, like I say, it was just using wireless communication, RFID technology. Excuse me. My final example of how we are using radio waves and wireless technology to help solve some of these grand challenges is a big-scale instrument. Now, we've been broadcasting radio waves into deep space and listening to radio waves from deep space for over 100 years now, since the days of Marconi. And that's allowed us to realise how much there is in the universe beyond what we think we know. So in the past decades, larger and more powerful instruments have been designed and built to look deeper and deeper into space. And I'm very fortunate to be working on building the next generation. The biggest and the most advanced, powerful radio telescope ever. It's called the Square Kilometre Array, or the SKA. Now the SKA will be made up of hundreds of thousands of antennas, and here you can see an artist's rendering of what it might look like, because it's not built yet. Nowhere near being built yet. But all of these antennas will be connected and spread across thousands of kilometres, but with a central core in Western Australia and then in a remote area in South Africa. Now the sheer size of this telescope will make it 50 times more sensitive than any other radio instrument ever. The SKA will be so sensitive, it will be able to detect an airport radar-like signal on a planet 10 light years away. 10 light years away. And the amount of data this SKA will generate is enormous. It's estimated that the dishes alone would generate 10 times the global internet traffic. The global internet traffic. It's huge. These small things down here, the dipoles, that will be working at a much lower frequency, so these will be working around 70 megahertz. It's hoped that these will work up to about 22, 24 gigahertz. If they get these to work, the dipoles, it's estimated that the amount of data generated from those could be up to 100 times the global internet traffic. So this supercomputer, and it has to be very super, is needed for this SKA. It will have to perform 10 to the 18 calculations per second in order to try and reduce and generate reduce the data that the SKA will generate. So trying to work it out in my head, I was like, wow, that sounds like a very big number. It's 3 million, the number of stars in 3 million of our own galaxies. So the number of stars in 3 million of the Milky Way galaxies is the number of calculations that this supercomputer is going to have to perform. They are representing huge, huge challenges for us. And we don't know how to fix it yet, we don't know how to do this yet. It's one of the reasons that I think that we all have a job to inspire the next generation of scientists and engineers. We need people to try and solve this sort of problem, to work on this problem. And if they don't know about science and engineering and the great opportunities, then they're probably never going to go into it. They're probably going to go into banking or something else. And we'll lose all the great engineers. I just want to pause here and think about why we have this problem of a lack of engineers going forward. Because I, for one, feel very lucky to work in an industry where I can look ahead and see the rising demand for my skill. Why do we have to work so hard to inspire the next generation of scientists and engineers? Wouldn't it be great to have an industry where young people are literally queuing up to join us. Not because they're being cajoled or pestered into thinking it's the right thing to do, but because they know, they've always known, about the great opportunities there are in science and engineering. Society, including children, have an understanding of what many professions do, such as medicine, because we all had first-hand experience of it somehow. So it's ironic that wireless communication and engineering is everywhere, but it's invisible because it's woven into the very fabric of everyday life. Many young people simply do not know what engineers do, and why should they if we aren't out there telling them and showing them how ingenious engineers actually can be. So I think it's very, very important that we all do this, especially myself and my colleagues. And it takes people outside of their comfort zones. People are very, very uncomfortable doing this because that's not what academics do, right? I mean, we teach people who want to be there. They've come to university to study, so largely they want to be there. And we do our research. And so a lot of academics feel very, very uncomfortable talking about this and talking to people. But I think it's something that increasingly we need to do more of, and definitely need to do it more with young children and make sure that they understand all of the opportunities there are in engineering. I digress again, sorry. The SKA, like I say, was representing huge, huge challenges. And similarly to what happened in the world of communication, wireless communication, the development of radio astronomical techniques has brought about a revolution in our understanding of the universe. There's practically no field of radio astronomy today that has not been affected by the analysis of information carried by these radio waves. From the study of planets to the discovery of the cosmic microwave background radiation. And of course, there's still hope that sooner or later, someone might be able to identify radio signals which will be able to tell us about extraterrestrial intelligence and the existence of this, established somewhere else in our galaxy. Therefore, widening the scope and the profound implications of Marconi's invention. Thank you very much. Now I'd love to take questions, please.